All right, this is 2-2. Super important topic today, the normal curve. The normal curve and normal distributions. Okay, what we're going to start with here is going through primarily just talking points, kind of some characteristics of the normal distribution that I think you should know, and then we'll do some stuff. Okay, a little preview when we get to like the problems that we'll do. There are two calculator tutorials that these rely upon heavily. The normal CDF and the inverse normal. You should check both of those out. Okay, I can't show you everything here, but those tutorials are waiting for you on Schoology, and you should check those out and make sure you're good to go. Normal curves are symmetric. They have a single peak. They take on that really distinct bell-shaped. Okay? That bell shape can be kind of wide, or it can be really skinny. It depends on sigma, right? Sigma is our mean. Mu is our mean. I think that's pronounced, I think that's how it's spelled. It's mu, kind of looks like a cursive U. And sigma. Now you might be thinking, from what you've seen so far, that wait a minute, mean and standard deviation, wasn't that x bar and s? There's a difference. It's not going to matter for quite a while, so don't worry about it. The big deal is x bar or mu, that you understand those, that's a mean, and s or sigma is talking about standard deviation. Really the only thing that I want you to see here is just this notation, if you ever see it. That n is specifying that the distribution you have is normal, and then it cites mu and sigma. I don't think there's anything else on here. This all stuff right here, the standard deviation, the distance from the center, and the change of curvature on either side. Just a little side note that you might find interesting. You may or may not have a calculus background at this point, and AP Stats is non-calculus based. But normal curves, if you were to graph them, where the standard deviation takes place, is right around an inflection point, where if you're looking at like the rate of change at a specific point of that curve, it's where you see the slope change in terms of the rate at which it's increasing or decreasing. Bottom line, if you're interested in that, we can talk a lot more, because stats at its core really is calc-based, and there's a lot of very interesting connections that you might find. If you're not a calc person, don't worry about it, doesn't matter. Bottom line, just know that notation. All right, here's some crazy stuff that goes on with the normal curve. Some percentages that are just like mind-blowing. Not really, but I like to think of them that way. So the empirical rule, which was listed above, states that within one standard deviation, you would find 68% of your data, approximately. Within 2 would be about 95. And 3, 99.7. Now don't forget that normal distributions are symmetric, so I'm going to draw the center in right here. This 68, you could split up 34 and 34. These are all percentages, by the way. I just don't want it to look really messy with having enough room. And then if I go right here and take the difference of 95 and 68, that's about 13 and a half. 2 to 3, I could take the difference of 99.7 and 95 and get 2.35. And then up Beyond 3 standard deviations and below, about 0.15. So those percentages as they relate to standard deviation would apply to every normal curve. In lesson 1, we talked about the idea of standardizing a distribution. If you take all of your data and switch it over to z-scores, if a distribution is normal, right, there's no reason to believe otherwise, right? You could standardize it. The normal curve is no exception. You've got the definition of a z-score right there, but this might be our favorite distribution that we ever use. Standard normal, okay? Shape, normal. Mean, 0. Standard deviation, 1. Okay? We'll use it a ton. Alright, so I'm going to use the empirical rule here a little bit, and then I'm going to get to number 4, and all of a sudden we're going to have problems. But we'll get that. We'll get to that when we get to it, if that made any sense. Alright, we're going to look at 1, 2, 3, 1, 2, and 3. Topic here is data on the heights of young women ages 18 to 24. Problem tells us that it's approximately normal with a mean of 64.5. I normally put these below, but space-wise I like it up here. And a standard deviation of 2.5, which means there's 1 above, 2 above, and oh yes, 3 above. And below, 62, 59.5, and 57. Okay, the units being inches. This problem is going to go right back to those percentages that we saw on the other page. Okay, what percent of women have heights between 62 and 72? Okay. Whoops, I forgot, 67 or more. I'm getting ahead of myself. 67 or more, okay, that would be right here, this part. That was 13.5. This part was 2.35. And we can't really see it, but way out here, that was 0.15. Right, now to show my work, I just got to add those numbers together. About 16%. Okay. Now let's go 62 to 72. Basically what I'm going to do is not quite. I don't want the 0.15 anymore. But I do want both of these 34s, which I could lump those together and say, 62 to 67, that's 68% of your data. 67 to 69.5, I want those 13.5%. And then I do want another 2.35 to get me up to 72, which puts me at 83.85%. Okay. Now read through number 4, and you'll see it poses a problem. The empirical rule is great, and all those percentages are great, but let me draw it out for you. 61.25 is not an increment of the standard deviation, right? I may want a piece of data that is 1.5 standard deviations away from the mean. That might be what I'm looking at, and that empirical rule doesn't really help. Okay? So here's what we end up with. I'm going to draw a new curve, centered at 64.5, and I'm not working on this increment of the standard deviation, so I'm not going to draw those in anymore. All I'm concerned about now is just kind of marking where I am, and 61.25 is like right here. We'll call that X. And I want to know the percent of women that have heights that are greater. Okay? That's a great picture of what I'm trying to find. All that shaded area, what proportion of the outcomes in a normal curve is that? Okay? Now, this is where it's possible you saw it in class, but this is a hugely important calculator tutorial. You need to go check out how to use the normal CDF feature. Okay? That's what the normal CDF feature does, is answers exactly this question. Okay? This one comes out to be about 0.903. But going from like a location over to some kind of percentile, whether it's percent above or percent below, that's what normal CDF does. Standard normal table. Here's really the only thing I'm going to tell you. We use our calculator instead. Okay? I think it's interesting for you to note that historically the table was a big deal. And as far as function, table A in the back of your book, and it'll be in your formula packet too, it does what the normal CDF feature does. They do the same thing. Okay. Calculators, for us, have kind of rendered this table obsolete. This is more on how to use it. You can just disregard. Right now, it's honestly just a big waste of space. I shouldn't even have it in here. If you're ever like kind of interested in how it works, I could show you, but I'm going to zoom in here and just get rid of it. There we go. But I'm not going to show you. I don't care if you don't know a single thing about the table. I care that you know how to use the normal CDF. Okay. What I'm going to do here is give you the work that you have to show. Okay. These are in z-scores, so the units are kind of interesting. But if you were to use the normal CDF feature, you, along with your answer, right, and I'll tell you right now, because if you've seen the calculator tutorial, you know the answer to this problem is 0.9177. Okay? But in your work, you have to show shape, center, location, spread, and you have to shade the appropriate side. Okay? The diagram that I'll show you, like right here, that if you just say that, all right, my mean is 0, all this is standard normal, by the way. Sigma is 1. The z-score I have is like right here. And I am looking for all of the outcomes that are over to the left side. That diagram that I just drew, okay, for a question like this, if you paired it with your answer, would be worth full credit. That diagram takes care of everything. All right? When you use the normal CDF feature, you need to just sketch the diagram. Okay? Get in the habit. In Chapter 2, you will do it a ton. Okay? So to answer this question, I'm going to use a distribution. That sketch shows that it's normal. It's standard normal, so again it's centered at 0. Has a standard deviation of 1. We are way down here at a z-score of negative 2.15, and I want all the data that would have a z-score bigger than that, which is lots of it. And then that answer would come from the normal CDF, and done. Option number 3 here, or problem number 3. Mean of 0. Sigma is 1. Now this just has a starting point and an ending point. Okay, so I should have on my sketch that negative 0.56 is a little bit below the center, and then 1.81. That's quite a bit above. And then I'm looking at these outcomes that are in between, which is about 67%. All right, these next two, okay, they use a different calculator feature. So make note of that. Still standard normal. But here's what's going on. The 20th percentile, if I were to sketch that in, that would be like right here, so that chunk is 0.2, and then I'm looking in terms of a z-score where I'm at. This is the exact opposite of what we did. Okay, the exact opposite. Different calculator feature for 4 and 5. All right, make a note to yourself here. This uses the feature called the inverse normal, and you should check that out and make sure you can use it. You would see here the z-score we are at is negative 0.84. All right, one more here. 5 would also be an inverse normal. Notice how I'm making a sketch with each one of these. Right, on all these, standard normal. Mu is 0, sigma is 1. I'm like right here. Right, I don't know where that is as a z-score. I know it's going to be positive because I'm above the center, but it's where 45% of the data is above. Well, again, I could use the inverse normal to figure out there that I'm at a z-score of 0.13. All right, I'm going to zoom back out here. On this tennis example, okay, these are back to normal CDF, right? Because what I'm looking for is a percentage. The only thing that's different here is context. So this again would be two normal curves. Mu is 115, sigma is 6, and the units are now miles per hour. And we want to know what chunk would be greater than 120. Right there, okay? The difference here is really when you go to the calculator, you can just change mu and sigma and you can leave it in the units of miles per hour. You don't have to standardize everything. Okay? You can if you want, but you don't need to. Down here, same deal. Same data. This is centered at 115 miles an hour. It says it's normal. Standard deviation 6. What chunk of his serves are going to be between 100 and 110? About 0.196. All I want to do in these last couple slides is talk through a normal probability plot. The interpretation, I think, is a big deal. You're not going to use your calculator to make one. Okay? Here's the bottom line. It gives you some kind of science experiment context about, density of the Earth. Here's the deal. You've got data that looks approximately normal, right? If you were to draw the density curve over it, looks pretty close, all right? From time to time, you can come across these normal probability plots, okay? I want you to know what they are. You're not going to make them. But we could, right? It's a scatter plot. And it's actually relatively simple. Over here, you have X. Over here, you have Z. It's a scatter plot that compares a piece's data to its z-score. It's really a pretty simple thing. Here's the deal. If it's linear, that would suggest that your data is normal. Okay, it's often kind of used to test to see if we think our data is normal. If you see something like this, where it's got this big tail to the right and the points are getting really spread out, and it doesn't follow a line, probably a right skew. Okay, if it looks more like this and the points are kind of spread out at the bottom, evidence that it's a left.